Good evening, everybody. I just want to write down what I remember from, I guess, abstract algebra. This set of objects here, I think, is called the integers with the square root of 10 adjoined. I believe I've heard that, and I hope this notation is correct. But if it's not, an element in this set, or this group, I guess, is of the form an integer plus an integer times the square root of 10. All right. Now it's its own set. It does include the integers. If n is 0, the integers are included in this group, if you want to call it that. And there's some things that are different about it. Number one, it doesn't enjoy uniqueness of prime representation. And number two, it has this notion of units. And just to be clear about what I'm talking about, we know that 1 divides n for all n a member of z. That makes 1 a unit, okay, for all n a member of z. And also minus 1 would be a unit. And those are the only two units in z. Okay, but today we're going to show that 3 plus the square root of 10, which sure doesn't look like what I would think of as a unit, is a divisor of every extended integer, which makes it a unit in z conjoined with square root of 10, okay? So let's get busy showing that. Now, so anyway, I took just a typical element in this thing called extended integers. And by the way, folks, I got this out of a number theory book by David Bressoud. An excellent number theory book with some great homework problems, much different problem set than what you see in the more current number theory textbooks. Okay, but we're trying to show that if you take a general extended integer, okay, and divide it by 3 plus root 10, you get another element in the set, another element in this form of m plus n square root of 10, okay? So let's take a look. The standard approach on that is to multiply through by conjugate, and we're just using the fact that a plus b times a minus b is equal to a squared minus b squared. A plus b times a minus b is equal to a squared minus b squared. Okay, standard algebraic identity that gets used a ton. All right, so that's what I did right here. Understand this entire object in parentheses is just 1. It's okay to multiply by unity, right? Okay, now, so when you do that, this minus 1 comes from the fact that 3, this is the same as 3 squared minus 10, right? We just use this result right here if you're wondering where that came from. This top part is just everything being expanded out. And y'all, what we're trying to show is that we will get something of this form. And that will prove that this object will divide everything just like 1 and minus 1 divides every integer in the regular set of integers, okay? So now I did a little bit more work here. Notice this minus sign will just change these signs around. You see how it was minus 10 in here, now it's plus 10 in. But notice right here that you can already see that we got what we wanted. We got an integer right here plus, if we take root 10 out of here, okay, what we get is root 10 times m minus 3n. So you see this is in the form, I'll just go ahead and complete right here, 10m minus 3m. So you see this makes this object an extended integer, okay? This is an extended integer. We got something in the original form, an integer plus an integer times root 10. Okay, so this is an extended integer, and I'll just abbreviate. Okay, extended integer because it is in this form of a regular integer plus an integer times root 10. That's exactly what this is. This object right here is an integer. This object is an integer times root 10. So that completes the proof. So we can write down QED. And I thought it was kind of interesting. And there's other units. This is just one. This is a homework problem from this guy's textbook. And I'll try to give a description of it, or give it more an account or a citation or whatever you want to call it in the description of this video. But I think it's kind of cool stuff. And again, this was a number theory book, but this is an abstract algebra concept, I think, where you adjoin an element that's not in the set to the set, and you create a set with the original structure plus some more structure. And again, the one thing I do want to point out is this set of extended integers. There's examples, I'm going to do a video on it, of where it has two different prime factorizations, okay, or it has a broader set of units than here. The units for the integers are just -1 and 1, you know. Here, this is 1, and there's plenty of others, by the way. This is just 1. I just showed you that this guy is a unit because it divides everything. And let's see, I think that's about it. I'll try to, I'm not sure if this is a group or not. It probably is, but I don't know if everything has a under multiplication. I'm not sure if it's a group, because I don't know if you have a multiplicative inverse or not. I'm going to study this stuff some more, though, because it's quite interesting. It helps you to appreciate the uniqueness of the prime factorization of the integers, because this is a structure that has a prime factorization. They're called indivisibles, by the way, just to worry about, so you won't have to worry about the ambiguity with prime numbers, but they're called indivisibles. And there's a lot of the numbers do not have unique prime representations. So I think every number can be written as the product of primes up to units, you know. But anyway, that does it, folks. Hope you enjoyed, and we'll get you. I think I'm going to do some more stuff like this from number theory and abstract algebra.